Good morning, fellow students, teachers, and parents. It is a great pleasure to welcome Professor David Gross to the new International School of Thailand as part of the Bridges series of lectures. Professor David Jonathan Gross was a 2004 Nobel laureate for physics from the University of California, Santa Barbara. The work of Professor Gross led to a completely new physical theory, quantum chromodynamics, which has been widely accepted to be the best understanding of how the universe works. His discovery of asymptotic freedom holds that the closer quarks are to each other, the less the strong interaction or color charge between them. Having recently completed atomic theory, we students would recognize some of the terms just mentioned. However, having just scratched the surface, the world of quantum physics still remains a mystery to us. Professor Gross's theory has brought physics one step closer to fulfilling a grand dream, to formulate a unified theory comprising gravity as well as a theory for everything. I am sure you will join me with a round of applause in giving the professor a warm next welcome.
Well, hello everybody. It's really delightful to be here at NIST. The NIST I know, of course, is in Washington, and it's the National Institute of Standards and Technology. But it's nice to be introduced to a new NIST. I haven't seen much of it except for the building and your eager faces, but I'm already quite impressed. I gather I'm going to say a few remarks about myself, about science, and then we can have a dialogue of questions. I'm sure there are many. I'm a theoretical physicist, as you heard in that very good introduction. I work with pencil and paper, trying to understand the basic constituents of matter, what makes up the world and how it works. And I'm sure many of you aren't really sure what you want to do with your lives. I was lucky to have decided to become a theoretical physicist at the age of 13, which is kind of young, but I got turned on by reading popular science books. And it just seemed so exciting to spend one's time trying to battle with nature and figure out the secrets of nature just using your mind. And I was lucky to go on in theoretical physics for the rest of my life, and it's been a lot of fun. I was very lucky to enter research, graduate school at Berkeley, and research at a time where elementary particle physics, the study of the smallest constituents of matter, was sort of at its height, and people were beginning to experimentally probe the structure of the nucleus, this tiny little center of atoms that at that time was totally mysterious. And that's the most exciting thing to follow in science, those areas where nobody really understands anything. And I was also lucky because at that time there were new experiments coming on that turned out to be the crucial ones that indeed revealed the structure of the protons and neutrons that make up the nucleus. And eventually led us to the crucial insights that provided us with a theory that you just heard briefly described, a theory of the nuclear force, a theory of the force that holds the nucleons together in the nucleus, that gives rise to the structure of all the nuclei of all the atoms that we know, and that actually explains that the nucleons themselves are made out of more fundamental objects, point-like objects called quarks, very strange particles with fractions of the charge of the electron that no one had ever seen. And in fact, one of the big mysteries was, why don't you see these quarks if you think they might make up the nucleons? And in the end, we explained that by this asymptotic freedom discovery that the force between the quarks, in a very special theory that we were therefore led to, has the remarkable property of changing as you vary the distance over which the force acts. So for example, when you look at the quarks moving very close together and over very short times are rattling around quite freely, the force is very weak. But if you try to pull them out, the force gets stronger as the quarks get farther apart, which is sort of counterintuitive, but is a consequence of the strange properties of quantum field theory, of the structure of the quantum vacuum. Anyway, that was almost 30 years ago. Takes the Swedish Academy a long time sometimes to recognize, especially theories, which the scientists are often skeptical about until they're proven by experiment, as it should be. And since then I've been, and my colleagues have been pushed to even more interesting questions about the ultimate structure of matter, of space, of time, and the beginning of the universe itself. And following, for the last 25 years or so, following a direction called string theory, which you might have heard about, a very ambitious attempt to construct a unified theory of all the forces, including gravity, which we haven't completed. In fact, we're pretty confused about a lot of the aspects of this theory and what it implies. And some of us, including me, suspect that we are going to have to make, or somebody probably, maybe one of you, some young person is going to have to come along with some change, serious changes in our concepts, basic concepts of the universe, including our understanding of the nature of space and time itself. So, I've had a very exciting life, and I just want to end by telling you a bit about trying to give you a sales talk for doing basic science. I mean, I'm sure many of you will be lawyers and businessmen and doctors, and there are many other careers. In fact, the number of people who do science and the number of people who do basic science is a small number, but it's a great life. And so I wanted to tell you a bit about that life and what it means to be a scientist, because to encourage those of you who really are interested in thinking about such a way of leading one's life, to stick to your guns and resist temptation. There are many wonderful advantages of being a scientist, but one of the greatest is that you get paid to do what you really love to do. If you love it, of course, as I do. The doing of science, the spending one's life exploring problems posed by nature, the mysteries of nature, which are so mysterious, and whose, when we finally understand those mysteries, it often is so beautiful, is just a great way of living. And in basic science especially, one often can be supported quite well, or reasonably well, to spend one's whole life doing interesting stuff. And that, is not so common in the world. Also, the life of science is a very social life in a way that I think most people don't totally realize. They think scientists are nerdy types that, live in isolation and aren't interested in anything except their equations, whatever they mean. But that's totally untrue. Scientists, in fact, are incredibly interactive, at least theorists like myself, because we really need continual dialogue with our fellow scientists, try out our ideas, and we work together and talk all the time and communicate. It's a very social activity. And not only do we do that in our universities or our laboratories, but we do that around the world. Science is like this school is incredibly international. So I'm now the director of an Institute of Theoretical Physics in Santa Barbara, where scientists from all over the world come together and spend weeks and months working together collaboratively on the most exciting areas of physics. And physics, we interpret very broadly. It's everything from cosmology, particle physics, the properties of ordinary matter, to biology now. And 40% of our visitors are from outside the United States. I travel around the world. Everywhere I go, I meet physicists, and we share not only a common language, but a common interest and a common culture. And I myself feel actually much more of a citizen of this community of scientists than I do sometimes in my own country. It is a wonderful thing, this community of scientists that has shared interests and goals, and although we often compete with each other to be the first to understand the mysteries of nature, we also are incredibly cooperative and collaborative. So it's a wonderful international community that one becomes part of when one becomes a scientist. But the main thing is just the love of doing the science. And I think maybe I should stop here and give you a chance to ask questions, and I can amplify on some of the points that I've missed if you want to push me. So let's open the door, and I'm sure, given the excellence of this school, that you're all used to being not shy and asking questions.
If you're not shy but you're quiet, might be fun.
As an example, how do you go about conducting experiments to find out theories? Like, how long a time does it
Well, she was asking how I go about conducting experiments. I'm a theorist. So in physics, there's a sort of a sharp division because of the complexity of big science, of science nowadays, between people who work in laboratories and do experiments and people who work on the blackboard or with pencil and paper and come up with models and theories and predictions, try to understand the experiments, or come up with new theories and suggest new experiments. So I'm a theorist. I work with mathematical symbols and blackboards, and I don't get dirty. I get covered with chalk. In my field, which is the study of elementary particles and that area of fundamental physics, the experiments are incredibly big, expensive, and they take a long time, and they involve many people. We are all awaiting, in my field, the construction of a new particle accelerator, a machine that accelerates protons around in a 20-mile long ring, bangs them together at incredibly high energies, and produces collisions out of which thousands of particles come, and then with massive detectors, which are about 5 stories high, analyze what comes out of those collisions to try to figure out what goes on at incredibly short distances. So those experimenters who do those experiments have been building the detectors for the new accelerator for the last 10 years or more. The groups that build the detectors and will do the experiments contain somewhere between 1,000 to 2,000 people. Each detector costs about $1 billion. The machine itself costs about $6 to $7 billion. It's taken about, the whole project has taken about 15 years, and we're all waiting for it to turn on. So that is the most far out example of big science. But as we push deeper and deeper into the nature of, and try to gain greater control over nature, not just in high energy physics, particle physics, but also in nanotechnology and nanoscience, it becomes, we need more expensive, bigger, and more exotic tools. So it's a massive effort, and which is why science requires people working together, sometimes in large teams. Theorists have it much easier. We still, except for the computer, which helps us a lot, pencil and paper remain our best tools. Over there, there's two.
Would you say that the grand unified theorem is the ultimate goal for study of particle physics?
Well, the question was, is the grand unified theory the ultimate goal for theoretical physics? The ultimate goal for theoretical physics is to answer the questions that we can't answer, to address the mysteries that nature still poses. We have learned over 2 centuries that greater understanding and greater predictive power follow from unification of the forces. So in the 19th century, people were studying electricity, and then they discovered magnetism. And then Maxwell finally understood that electricity and magnetism were just part of the same thing. We now say electromagnetism. But it's really the same thing. It's a unified theory of electricity and magnetism. And in the 20th century, we're beginning to unify the nuclear forces together with this picture. And they seem to fit together. The clues are overwhelmingly strong that they are unified. But to truly understand that unification, one has to look at very short distances. Much smaller than the atom, much smaller than the nucleon, much smaller than the quark, it seems.
And it will go on forever, it seems.
And, well, and in this theory called string theory that I now work on, the unification of those forces that govern the behavior of atoms and nuclei is also unified with gravity, the 4th force in nature. If we were to achieve such a unification and be successful and have confirmation from experiment that it was correct, we would have a grand unified theory. That might be the end. Probably not. Probably there are new questions, and we would, as you say, go on. Shall we go on forever? Who knows? Maybe, maybe not. But we're certainly going to go on for quite a while, and the questions we can't answer today are enormous and many. And unification seems to be a good way to approach those questions.
And with the study of the small particles, are there any pragmatic use of this in real life?
Well, of course, one is always asked that question, and the simple answer is not any that I can think of. By the way, it is very nice, in a sense, to be in a field which has no pragmatic uses. It saves one from corruption of the soul and interference of the politicians. But of course it makes it harder to get funding. However, it is very dangerous to try to predict applications and technology that might emerge from basic science. The famous joke is Michael Faraday, who was one of the discoverers of the phenomena of electricity and magnetism. And there's a story that Queen Victoria visited Faraday's laboratory, and he showed her magnets, and he showed her that you could induce an electrical current in a circuit by moving a magnet through it nearby. And she was very impressed. And she said, "This is very impressive, Mr. Faraday, but what is it good for?" Which is your question. And he said, "Ma'am, I have no idea. But when we figure it out, you will tax it." And of course, electricity and magnetism were the basis of the Industrial Revolution and all of civil, technology ever since. In the earlier in the 20th century, people who were interested in fundamental physics, theoretical physicists like Bohr and Einstein and Heisenberg and Schrödinger were inventing quantum mechanics, the strange laws that govern atoms. And they had absolutely no idea what that was good for. They just wanted to understand how the atom works and how the world works in this strange quantum mechanical sense. And they couldn't have predicted that modern technology is more and more based on our cell phone, this thing, on quantum devices. And that the forefront of modern technology is possible because of our growing control over the quantum world. So I can't predict what the applications of our understanding of how the nucleus works will affect technology, but it's very dangerous to predict that in 100 years from now, there won't be such application. So there's lots of things.
Could you please explain your theory in more detail?
Well, that would take me at least 10 minutes.
How about that?
Now, it would take a little longer. In some sense, it is a kind of generalization of electricity and magnetism. The first fundamental theory we had of forces was Newton's theory of gravity. The second was the theory of electricity and magnetism, which sort of explained that there are the constituents of matter, like the electron, have an electric charge, and that gives rise to a force between charges. The force being transmitted by the electromagnetic field. Right? It turns out that the theory of the nuclear force, the force between quarks, is a kind of generalization of that. The difference being that QCD, quantum chromodynamics, is a little more complicated and much richer because of that. The quarks don't only have one kind of charge, they have three kinds of charge. We call them colors, but they're just three kinds of charge. A, B, C, red, white, blue, whatever you want. And their forces between the quarks are transmitted by a more complicated field of force. And that gives rise, because of the strange quantum mechanical properties of the world, to a force force which is very different in nature. It has this property that it gets weak. The charges effectively weaken when the quarks are close together. These three charges. And get strong when you try to pull the quarks out. To go beyond that explanation would take a little bit more time.
Maybe a personal project for later. Can a champion's just put the mic?
Not to put you on the spot or anything here, but I've always wondered what a great, scientist's view on ultimate being, kind of like the religion kind of, thing.
Well, I usually try to avoid answering those questions. Some places in the United States you could get lynched if you give the wrong answer. But I'm, pretty close to being an atheist. I don't, as one scientist said, I don't see a need for God in my equations. But I like to distinguish between questions that are scientific questions and questions that are ascientific questions. So I might be agnostic. The question of questions that are addressed by religion are not ones that science, or most questions addressed by religion, are not ones that science can directly address by experiment, observation, or analytical thinking, reasoning. What I've noticed reading the history of science is that many questions that used to be answered by religious arguments and faith become scientific questions and then are outside of religion. Such as, how did the earth come into being? Or how did life begin and what is life? And many of the questions maybe haven't yet been answered, but are valid scientific questions that we now ask and study, like, what is the nature of the mind? But there's still always questions that are sort of beyond science at the moment. And partly the issue here is, again, will that go on forever? Will all questions, even questions like, how did the universe begin? What was time before time began in the Big Bang? Questions like that, which we're beginning to address. Will they ever be all scientific and addressable? I suspect yes, but I don't know. So in that sense, I'm still agnostic.
Thank you.
Since you're in the research department, did you ever run the risk of running out of funding?
Well, it's worse than that. I'm the director of an institute where we have 1,000 visitors a year, and we need always more funding. So, any scientist will tell you that they are always short on funding. But, that's part of life. You have to, I think it's an excellent system in theory, although I sometimes suffer from it, that you have to compete for funds because it's in that competition. As long as the decisions are made by scientists, that good administration of taxpayers' money is made. So by and large, the system works very well. And by and large, good science, at least in the United States, Europe, is well funded and efficiently managed. But any scientist will tell you that they always need more money, and I will tell you that too, especially if you have some.
You earlier said that quarks could not be observed.
Yes.
While formulating a theory, how did you know that when the quark became closer, they...
Well, it depends what you mean observed. If you think about it, the only thing you observe are photons that hit your retina, and from that you reconstruct a model, a picture of the whole world. What I meant by quarks not being observed is the following. If you take an atom and you hit an atom, say with another atom, hard, an electron, which is a part of the constituents of the atom, an electron will come out. And you can use that for electron beams and to make television tubes and so on. But if you hit the proton real hard, quarks don't come out. You can never get them out far away from the other quarks. They're bound, confined together. However, you can still see them. In these experiments that were very crucial, you hit a proton with an electron, and by seeing how it bounced off, you could translate that into a sort of a very sharp snapshot of what the proton looked like for very short times. And those snapshots indicated that over these very short times that it looked like the proton was made out of quarks that were moving around very easily. At least that was one interpretation, and that led us to the understanding. But today, you know, if you walk into a big particle experimental control room where experimenters are seated in front of computer screens reading off the output of their big detectors. So they see pictures that describe what goes on in their detectors because of these collisions. They have in their displays measurements of the energy of particles going out in all sorts of different directions, the energy and momentum, and they will point to the screen and say, there's a quark, and there's another quark, and there's a gluon. They can see the quarks. Now, of course, they see them because they have this theory in mind, which tells you that, well, there were quarks there, and they went out carrying a lot of energy and eventually turned into a jet of particles. And what the detectors detected was the jet, but what the experimenter sees, using his model based on our theory, is a quark. But that, by the way, is the same way you see an electron. You don't see the electron directly. You see the photons that the electron produces. From that, you deduce or see an electron. So seeing is believing, and believing is seeing. You need a model. You need a way of translating the primary visual data or other data into a picture.
What is the basic concept of the superstring theory?
Well, actually, we're not totally sure. But one of the, probably still the best way of describing string theory is just the idea that all particles are not really particles. They're different vibrations of a single string-like object. So, you know, physics for centuries has been based on the idea that things are made out of particles, and some of those particles have structure, like the proton, and it's made out of even smaller particles, and so on and so on. But string theory says particles are made out of different vibrations of the same string. So a string is an extended object, right? It's not a point, but a line that closes on itself. And that string can vibrate just like a violin string. So if you have a string, a violin string, you can have many modes of vibration. And each of the vibrating modes of a string will look to us, because we can't really see that small, the size of the string, will look to us like a different particle. And one of the exciting things about these string theories that we discovered in constructing them was that they naturally contain all the particles we need. The particles that make up matter, particles like quarks, electrons, and the quanta, the particles of the force themselves. Like the quanta of light, the photon that is the transmitter, transmits the electromagnetic force. The force of electricity is associated with a particle. It's called light rays, or whose quantized form are particles, photons. And the other forces, the weak and strong nuclear forces, are also transmitted by particles, which in string theory are different vibrational modes of the same string. And the force of gravity is transmitted by a particle called the graviton, which again appears as a different vibrational mode of the same string. So string theory is very, from the beginning, a very unifying theory. There's one string-like object, vibrates in an infinite number of modes. And among those vibrating modes, the lightest ones, the ones we would have had a chance of seeing so far, more or less correspond to the ones we've actually observed or deduced in nature. So that's one way of describing string theory in a nutshell.
Just before we come back to someone who's already had a question, anybody who didn't ask a question yet? Just you're all on the mic.
Thank you. I have a question. As we go into the 21st century, and we have more advances in this area of physics and superstring theory, in grand unified theory, where do you think these advances are going to come from? Where is the most interesting research happening in the world right now? And what areas of the world are going to be important for this research?
Well, there are many areas of science and physics that are advancing rapidly, but you asked specifically about high-energy physics or string theory or unification. That field is extremely international. The experimental centers, as I remarked, are enormous, expensive, and require the collaboration of many, many countries. So the next big experimental facility that is going to start next year is being built in CERN, which is a European consortium of nations, but it involves non-European countries as well, and the United States is a big contributor. It is, and the people who work there come from all over the world. And other facilities like that exist in around the world, but anything, future developments will forever, from now on, always be worldwide in their scope. As far as theoretical research goes, it has always been, again, international in the sense that even though, say, the United States is a very important center of research, the people who actually work in the research centers are at least 50% from outside the United States. So many of them come together at these major research centers but they're certainly not just American. And similar research centers in theoretical physics are growing rapidly in other parts of the world, especially in Asia nowadays, and especially in China, whose economy is growing rapidly and has decided that they will be a major scientific research center in the 21st century. Not just a user of advanced technology, but a producer of new ideas and new basic science which drives that technology. So if you ask me if I look 50 years from now, I would say that countries like the United States and European countries will not be as dominant as they are today as the centers of international collaboration, but there will be, it'll be much more spread out, and certainly a large part of the growth will be in Asia. Well, as I said, that's one of the advantages of working in very basic science. It's also one of the advantages is that there are no practical applications like bombs. One of the disadvantages is there's no practical applications like a cure for the energy crisis. So, if you ask me directly how basic research in fundamental physics contributes to peace, I would point to the example of international cooperation that science gives to the world. Because science is providing an example of internationalism that is unique. From the beginning, it was always understood by scientists, that science was international. After all, we're addressing questions posed by nature and not by Parliament. And the judge of our theories and our discoveries, are we right or wrong, is not politics or religion. So science has been from the beginning one of the most open, democratic, non-authoritarian aspects of human culture. And it, I believe, has fostered democracy and open societies around the world. It is not an accident that in the Soviet Union, one of the leading advocates of human rights and democracy were people like Andrei Sakharov, who was a basic theoretical physicist interested in basic science. Because that part of Soviet society was the most open and democratic and active in promoting human rights and democracy and peace. So I think if you ask me what is one of the most important goals, little talked about in the world, it is to arrive eventually at the situation where we have one nation, one planet. It's kind of absurd, if you think about it, to have these separations, which make less and less sense from almost any point of view and cause so much problems. And we're now faced with problems, not just of war and peace, but of sustainable economies and energy usage and the health of our planet that transcend all national boundaries and are not going to be solved probably without a true international law, international government. It's hard for me to believe that in 1,000 years from now, and every once in a while I like to look, instead of just 10, 50 years from now, and try to imagine the world 1,000 years from now, assuming we survive. But imagine coming back in 1,000 years from now, do you really think that we're going to be running the world with 150 little nations? It just doesn't make much sense. And I have a feeling that in that inevitable drive towards regarding ourselves, I mean, we've learned in the last few decades that we all have a common mother, right, who lived 150,000 years ago. I think we, in 1,000 years from now, will have a common government. We'll all be citizens of the planet. And I think science provides an example of that kind of culture and will help us move in that direction.
Going back to string theory, how does string theory propose to solve the problem of defying gravity with the other forces when other theories have failed in the last?
Well, it just does. You know, string theory was accidentally discovered in an attempt to understand the nuclear force. It turns out when you pull quarks apart, the reason you can't get them out of the proton is that, in effect, a string develops between them. The electromagnetic field, the color fields, the chromodynamic fields, are confined to a flux tube which looks like a string. So people accidentally discovered this thing we call string theory, which we don't fully understand yet, by trying to understand the nuclear force. They were not trying to unify the forces, and they were not trying to understand gravity. And they discovered in exploring this theory that it contained gravity. So, and it contained gravity in a way that was nice and free of all the problems that you have if you try to directly take Einstein's theory of gravity and quantize it, make it consistent with quantum mechanics. So, it just happened. We can understand a bit of why it happens, but it just happened, and it happened at a time where people weren't happy about the fact that it did that, because they didn't want to find a theory of gravity. They wanted to find a theory of the nuclear force. So it is a remarkable feature of this theory that was stumbled into, accidentally discovered 40 years ago, and we're still exploring.
One quick question. If I went to UC Berkeley 20 years ago, I would learn that field theory equals to Feynman's equation. Right now, if I go to UC Berkeley, would I learn that particle physics equals to asymptotic freedom?
Well, no, you would learn that the strong force, the strong interactions, are equals quantum chromodynamics, which of course, whose secret is asymptotic freedom. You might also learn that particle physics equals string theory. At least from half of the faculty at Berkeley.
That was a quick question. I'd just like to come up and thank you. I was about to say this is the first time that I understood what string theory was until the penultimate question. Then it went all upside down again and I lost it completely. But just as the ultimate aim of science and physics is a unified theory of everything, the ultimate aim of a school is to create lifelong learners. And what's great as a teacher is to actually see an example of a real, live, and ultimate lifelong learning. That idea of being comfortable with knowing, and really uncomfortable at not knowing, and needing to strive and inquire, and all those things that we talk about a lot with our learner profile at school. So it's been a fantastic opportunity. I think whether you are and consider yourself to be a scientist or not, the fact that you delved into the depths of physics, but also connected very much to the real world and the issues that we're all facing. And I love the idea of coming back in 1,000 years' time and thinking about that for the rest of the day. It's an amazing opportunity after a holiday to come in and have such a rich academic diet on the first day back. So I hope that you've enjoyed it and that you appreciate it. And a number of you I know will be flooded with questions and wanting to do research. For others, it's probably, like me, more than enough to try and go and understand string theory. I'd like to say on behalf of this, Dr. Professor Gomes, thank you very, very much. Well, and the rest of your tour. Probably wait for a sit down. Thank you very much. So, I'd just like to ask students in the first two rows, can you stay